Physics for everyone welcomes you. Important aspects of Coulomb's law. Let us learn Coulomb's law. Then next we learn all the important aspects of Coulomb's law. Here, this is a well-known diagram, well-known formula that we have learned earlier. Right? Let us read this Coulomb's law once again. The force of interaction, that is attraction or repulsion between two stationary point charges in vacuum, is directly proportional to the product of the charges and inversely proportional to the square of the distance between them. Mathematically, F equals K times Q1 Q2 divided by R square. Let us go with the first aspect of Coulomb's law. Coulomb's law states that the electrostatic force is directly proportional to the product of the magnitude of the 2 point charges, mathematically F proportional to Q1, Q2, and the same force inversely proportional to the square of the distance between the 2 point charges, mathematically F proportional to 1 by R square. Good. F, this is nothing but the magnitude of the force, that is equal to Q1, Q2, it's nothing but the product of the two charges divided by R square, nothing but the square of the distance between the 2 point charges. The unit is Newton. Second aspect, the electric force is a conservative force. That means the work done against this conservative force does not depend upon the path followed. So there is a definite relation between the conservative force and the potential energy of the system. So F equals minus d epsilon by dx. Look at the diagram. Coulomb's force is a central force. That means this force acts along the line joining the two center of the two bodies. F21 and F12 always acts along the line joining the two charges. Fourth one, SI unit and dimensional formula of permittivity. The value of K equals 1 by 4 pi epsilon naught. The numerical value of K is 9 into 10 power 9 Newton meter square Coulomb power minus 2. Here epsilon naught is the permittivity of the free space or vacuum, and its value is epsilon naught equals 8.85 into 10 power minus 12 Coulomb square Newton power minus 1 meter power minus 2. The SI unit of permittivity is Coulomb square Newton power minus 1 meter power minus 2. Let us learn the dimensional formula of permittivity. Let us take the unit Coulomb square Newton power minus 1 meter power minus 2. Let us substitute the dimensional formula of Coulomb, Newton and meter, and let us check out the dimensional formula of permittivity equals AT, that is the dimensional formula of Coulomb, m L T power minus 1, that is the dimensional formula of Newton, then L, that is the dimensional formula of meter, right? So after simplifying, we get the dimensional formula of permittivity equals m power minus 1, L power minus 3, T power minus 4, A power 2. Effect of medium on the Coulomb's force. So here you have the air medium, in that the two charges are separated by distance R is placed. The force between these two charges in air or vacuum equals 1 by 4 pi epsilon naught Q1 Q2 by R square. The same one now placed, the same system is now placed in a medium, right? Okay, now you get a new force. That force is given by a formula Fm equals 1 by 4 pi epsilon Q1 Q2 by R square. As we know very clearly, the permittivity of the medium is always greater than the permittivity of free space. So definitely the force in the medium is always less than the force in the vacuum. The relative permittivity, otherwise called dielectric constant K, for a given medium is given by epsilon r equals epsilon by epsilon naught. So the relative permittivity is the ratio of permittivity of the medium to permittivity of the free space. So epsilon r for vacuum is exactly 1. For air, it's little, very, very little higher than 1, 1.00054. For water, it is 80, and any other medium other than air and vacuum, it's always greater than 1. So any other medium other than air and vacuum, the force between the two charges always less than compared to as they were in air or vacuum. So epsilon r is nearly constant. This epsilon r depends upon the nature of the medium and magnitude of the charge. Epsilon r has no unit. Now let us go with 1 coulomb. Look at the diagram. The 2 point charges now becomes 1 coulomb each, and they are separated by a distance of 1 meter placed in air. So with this condition, let us find what is the magnitude of the force available on the each charge. The magnitude of the electrostatic force between the two charges, each of 1 coulomb and separated by a distance of 1 meter in vacuum, is calculated. So F equals 9 into 10 power 9, that is the value of K into Q1 Q2, that is replaced by 1 into 1 divided by R square, that is replaced by 1 square. The final answer is 9 into 10 power 9 Newton. Right? Good. This is a huge quantity, almost equivalent to the weight of 1 million ton. We never come across 1 coulomb of charge in practice. Most of the electrical phenomena in day-to-day life involves electrical charges of the order of microcoulomb or nanocoulomb. Electrostatic force obeys Newton's third law. So let us start with the first force, that is the force on first charge due to the second charge. So F12 vector equals 1 by 4 pi epsilon naught Q1 Q2 divided by R21 square R21 cap. And we know that very clearly that R21 cap and R12 cap are equal in magnitude but opposite in direction. Mathematically, R21 cap equals minus R12 cap. So in the right hand side of the first expression, right, we replace R21 cap by minus R12 cap. Remember, the magnitude of R21 square and R12 square are same. So F12 vector equals minus 1 by 4 pi epsilon naught Q1 Q2 by R12 square R12 cap. So the right hand side minus F21 cap. So F12 vector equals minus F21 vector. So electrostatic force obeys Newton's third law. Here, it's an electron. Each one is an electron separated by a distance of 1 meter, right, in a given medium, maybe air medium. Now the same electron with the mass Me, right, separated by a distance of 1 meter in the same medium. Good. So in the first diagram, it experiences electrical force. In the second diagram, it experiences a gravitational force. Now we are going to compare the ratio of these two forces, right? Good. The charge of the electron is 1.6 into 10 power minus 19 coulomb. The mass of the electron is 9.1 into 10 power minus 31 kg. Please remember it. Fe by Fg equals 1.7 into 10 power 43. The ratio of Fe to Fg between two electrons separated by a distance of 1 meter is given here. The Fg value is usually neglected while studying the Fe between electric charges because Fg is negligible compared to Fe. That's a conclusion. The expression for Coulomb force is truly for point charges. The point charge is an ideal concept. So in practice, charges are always associated with matter which occupies certain volume. To simplify the situation, usually a charge replaced by a charge of equal magnitude considered to be concentrated at a single point. Such a charge is called point charge. Coulomb's discovered his law by considering the charged spheres in the torsional balance as a point charge. The distance between the two charged spheres is much greater than the radii of the spheres. F1 is one electrical force, F2 is another electrical force. They have an angle theta. The second force is moved so that its tails meets the head of the first vector, and let us connect the tail of the first vector to the head of the second vector. We get the resultant force F net, which makes an angle alpha with the F1. Magnitude of the resultant of two electrical forces F1 vector and F2 vector F net equals root of F1 square plus F2 square plus 2 F1 F2 cos alpha. Sorry, cos theta. Tan alpha equals F2 sin theta divided by F1 plus F2 cos theta. The electrical force between the 2 point charges is independent of the other charges present in the system. So let us learn the principle of superposition. The electric force on a charged particle is due to the other charges is the vector sum of the forces due to individual charges. The electrical force on a charged particle is due to the other charges is the vector sum of the force due to the individual charges. So mathematically, F net vector equals F1 vector plus F2 vector plus F3 vector plus dot dot dot. So here comes a comparison between gravitational force and electrical force. Let us learn the similarity first. The gravitational force acts between the objects of masses. The electrical force acts between objects of charges. Fg proportional to m1 m2, Fe proportional to q1 q2, Fg proportional to 1 by r square, Fe proportional to 1 by r square. Fg is a central force. Similarly, Fe is also a central force. Central force means they act along the line joining the center of the two bodies. Fg and Fe, the gravitational force and electrical force, both are conservative force. The conservative force means the work done against these forces does not depend on the path followed. Let us now learn the dissimilarities between the gravitational force and electrical force. Fg is always attractive. Fe can be attractive or repulsive. If the two charges are like charges, then there will be a repulsion. Unlike charges means there will be attraction. Fg is very weak unless one of the body is very large. We can't find a gravitational force between two nearby balls, but there is a big and a large force between Earth and a single ball, right? Good. Fe is very strong, but it is not normally noticed as the charges cancel out within the body itself. Fg is independent of the medium. Fe is dependent on the medium. The G is independent of the medium. That is why the G is called universal gravitational constant. Epsilon, the permittivity, dependent on the medium. The G value is 6.67 into 10 power minus 11 Newton meter square kilogram power minus 2, which is very less than the K. So the gravitational force is very less. The value of K is 9 into 10 power 9 Newton meter square Coulomb power minus 2, which is very large compared to G. So electrical force is large. Coulomb's law is valid at a distance greater than 10 power minus 15 meter. A distance which is less than 10 power minus 15 meter where the nuclear force dominate. Fundamental forces in descending order, in decreasing order. First nuclear force, that is greater than the electrostatic force, that is greater than the weak nuclear force, that is greater than the gravitational force. Thank you, children.